So yeah, this webinar is on big data analytics for engineers. I'm Fred Kim. I'm in charge of product management for signal processing and analytics tools at Printsy. So what we're going to see during this next half an hour or so, an introduction to Printsy, allow me just a few slides, and big data, what do we call big data? Then a fundamental question, right? Is big data really of any use for reliability and durability engineers? In other words, is it just like in the territory of data scientists, or can we, as I don't know, test engineers, durability engineers, can we make use of big data? So we'll see why the answer should be yes. You know, the big benefits in having access to big data and extracting useful informations. So we'll see then the challenges in big data analytics or analysis, and we'll see how nCodeDS can help solve those challenges. We'll end up with a live demo that myself and my colleague Tudor, I'll introduce you to him next. We'll do those live demos, 2 demos, and a question and answer session. So let's start with this introduction slide on Printsy first. You know, Printsy is all about empowering engineers to avoid the cost of unexpected failures. And this is by using our software and our related services to deliver reliable products. Some of you know one or 2 of our software brands. So we got Encode for durability analysis, fatigue, and we got ReliaSoft for reliability analysis. And we also offer related services such as training, consulting, and material characterization. So that's Printsy. Now, your problem is that the data volumes in engineering are increasing constantly, right? And the main question is, how do we get value from all that data? So wherever you are in the industry, you're going to be facing this challenge, right? So here are a few examples illustrating how much data can be collected in various industries. So we got wind energy here, electric power generation, automotive, aerospace, healthcare, and in all cases, we've got huge volumes of data, but we want, first of all, to extract value from those huge volumes of data, whether it is, depending, what your job is, but value can mean to you increasing the effectiveness of the maintenance, or redesign. You want to redesign. You want to do iterations, design iterations on a component to make sure it's fit for purpose. You want to run tests maybe, and you want those tests to be realistic by taking into account the real usage maybe. So we want value out of these huge volumes of data. There's also a variety of data because of multiple sources. It's not just test and measurement. It's all sorts of sources and a lot of variability in this data. And by the way, one would want to quantify maybe this variability when we talk usage data, for instance. And there's something has to be kept in mind is this data, due to the variety, different sources, etc., is not necessarily perfect high quality data, right? So there's lots of potential issues, and the data may need to be corrected, all the issues fixed before processing. All of this needs to happen at high velocity, right? So those are 6 V's that are commonly seen in the world of big data. They characterize typically the big data. So now I'm an engineer. Why should I make use of big data? Well, when we discuss around with our customers, we see that it's quite important to have access to the product usage. So we want to capture variability in the usage severity, right, of our products. This will help answering the question. To answer the question, is the existing design, is it fit for purpose? But also it gives good indications on which feature of the product is used, which is maybe overlooked, which is misused, etc. Another big application of big data for reliability engineers this time is to ensure reliability, availability, maintainability, and safety. So, for instance, you got a recurring problem, and you want to understand the root cause of that problem using sensor data, based on historical data and with a model in mind that you want to implement. You can predict or attempt to predict upcoming failures. And the nice thing is, I just mentioned the model. You can test your hypothesis, your assumptions, by using the big data, the historical data that is available through the big data system. So those are two applications we hear a lot about, but both have the common denominator, or the common objective, which is to make decisions based on real facts, as opposed to assumptions or guesses or experience. And so now we want real fact. You want to quantify these, and based on that, you want to change your maintenance strategy or redesign your component, or do more realistic tests, etc. Now the challenges. The first challenge here is the ability to cope with those huge amounts of sensor data. I insist on the word sensor data, because we're not talking here, financial or website visits or whatever. We're talking about measurements. So time series containing hundreds of thousands, millions, billions of data points, right? And representing the evolution in time of physical quantities, whether it's temperature, force, strain gauge, or accelerometer, microphone data, etc., etc. And typically an asset that you monitor, your instruments, right, contains tens, hundreds, thousands of channels of such time series, right? In the examples I showed 2 slides below, there was no application that was with less than hundreds of channels, right? And so therefore, performance and scalability are of primary concern here, right? Because you can imagine how quickly you can get overflooded with data. The second challenge is ensure data quality and cleanliness. So we want this data to be trusted, and therefore the results we obtained to be trusted, reliable. It's probably worth mentioning that veracity. So this V, veracity, is often more important than volume. There's no point having huge volumes of data if you can't trust the data. It's full of anomalies, and to the point it may as well become useless. So you'd rather have less data but more reliable sort of data than large data sets of unusable stuff. So anomalies, NaN stands for not a number. Those sorts of values must be identified upstream and corrected before running any analysis. That's very important. So this little sketch here represents, on the top line, horizontal line represents the garbage in, garbage out. So you've got raw data that you do not correct or take as it is for your analysis. So you'll end up with false positives, false negatives, inconsistencies in the results, anomalies in the results, right? Inefficiencies, generally speaking. Whereas if you include a cleaning process up front, then you'll have quality results. It's ready for further processing. It's, the metrics you're going to get out of it are reliable. You can count and trust on them. The predictions you're going to make are reliable too. You can run mining efficiently. And it's also ready for simulation, whether we're talking a CAE or tests or whatever. You can reproduce what you've the results on your simulation bench with the high confidence. The third challenge is the need for specific engineering analytics. Again, I'm insisting on one word here, which is engineering. So as engineers, we're trying to solve engineering problems, right? So we need to do specific analysis, like descriptive analytics. So we want to compute metrics, indicators, again, engineering metrics or indicators. So it could be the max temperature or an average, but it could also be an RMS if you're into vibration, or a spectrum, or a waterfall of spectra, and see the evolution of that. It may as well be a time at level histogram and its evolution again. It could be relative damage. So those are metrics that are really linked with specific engineering applications, right? You may want to do diagnostic analytics. So in other words, understand why a physical phenomenon, typically a failure, occurred. Again, you will want to use some tools, correlation tools, or very specific engineering tools to understand and find out the whys. And you want to also, you may want to predict the remaining useful life, RUL, or some maintenance related actions. When should I provision my maintenance parts, my maintenance team? When should it be ready, etc., based on predictions that you're making. These predictions, but it's true for descriptive and diagnostic analytics as well. You want to use historical sensor data that's available to you through the big data system you're using. You want to use contextual data like metadata, generally speaking. And as engineers, we like to use physics of failure and not only rely on statistical approaches, right? So adding this magic powder that are called, the physics of failure that are called magic powder on top of the process will definitely help you to get a better, sooner and with more meaningful, in a more meaningful fashion to the results you expect. So it's very important to have those engineering algorithms, if you like, which enable you to use not only the sensor data, not only metadata, but also physics of failure, fatigue, for instance, right? So in terms of products now, we have Akira. You probably have heard of Akira. It's a powerful product for it's a web platform for democratization. So let me tell you, typically, or historically, or traditionally, the data sources were coming from test and measurement exercises or for CAE simulation. And we would traditionally use desktop tools such as Design Life for CAE fatigue, GlyphWorks, Vibesys for signal processing, whether in durability applications or vibration acoustics. And now with Akira, we can do the same, but now server side. So it's a web-based platform you can access in an enterprise fashion, and you can create apps to make a complex workflow easily accessible to anyone in the company, right? Not having to be an expert in the software in question. We've got data search and indexing capabilities in Akira, making, again, searching data easier. We got a good way to manage license with licensing benefits in Akira, and the analysis that you eventually run is happening on server side, right? So you can have a very powerful server and run your analysis via apps and data search, from your local computer, which may not be a very powerful processing computer, right? Now, on top of that, we've got nCodeDS. nCodeDS is the analytics engine of Akira. It can be used to process test and measurement data very efficiently, but it was also designed also to being able to address the needs of connected equipment data. So we're talking CAN data in the automotive world, bus data, generally speaking, or we're talking also big data here. So nCodeDS, as we'll see in the next slide, is available in Akira. It's a server-side, scalable processing engine. It's callable in Python, making it very flexible, easy to use, powerful. It's ideal for the batch processing of huge time series data sets. So it's really been developed for the processing of time series data, primarily columns of data. It's got no problems with unevenly spaced data with holes in it, data with not a number. It can cope with different algorithms to replace nans, it can produce the stats, histograms, whatever on unevenly spaced data. Things that the traditional tools, desktop tools, don't do easily. And in terms of analysis capabilities, it's got all the typical engineering algorithms, FFTs, stats, a lot of histograms, cycle counting, time at level, etc. that you can use, off the shelf. So the idea with nCodeDS is you get large quantities of sensor data and you turn that into engineering decisions as quick as possible. That's the idea. So how can nCodeDS help resolve the big data challenges that we mentioned a few minutes ago, right? So remember the first challenge was how to cope with loads, huge volumes of data. So nCodeDS is, as you can guess, very, very fast. So this little sketch illustrates a processing framework. It consists of inputs, analysis, displays, and outputs. All this could happen in Akira, right? Typically happens in Akira, right? And nCodeDS being standing in the middle, it's being the analytics engine. So nCodeDS is scalable. It uses very effectively the multiple CPU cores that are on the server machine. It can distribute the analysis on a file by file, for instance, basis that's managed by Akira. So you'd run in parallel, and it's lightweight. The data is streamed through the processing network, right? And it's the way it works. It's like the data is it's broken down into relatively small chunks that we call frames, and all this enables to limit the amount of memory that's used. Talking about the data, so the data can be streamed in nCodeDS like live data, right? Most applications use flat files. Those files can be indexed by Akira for later search. So CSV files or the text files like text format files like Parquet, for instance, or binary files from the usual data acquisition systems. But the input data can also come from various databases, such as a historian database. And the fact that nCodeDS is called in Python, it enables full flexibility. So one can connect to the database through its API, for instance, and get the data in and out. One of the demos is going to use data from a historian database called InfluxDB. And another demo, the one I'll do is using CSV files, flat files. So the other challenge that we are addressing is the ability to use advanced engineering algorithms, all this within an engineering workflow. So nCodeDS has all the pedigree that Encode has, right? So we've got a large set of well-known engineering algorithms, and the fact that you can use Python to glue them, you construct your workflow and achieve a complex engineering operation. So in terms of analysis, you can slice and dice the data to narrow it down to what, exactly the condition you want. For instance, we can we can extract sections of data corresponding to user-defined logical conditions, right? When the vehicle speed has exceeded this value and the gear was in this position and this or that, etc. And you can really narrow it down to exactly what you're after. We've got stats, all sorts of running statistics, ranked stats, as well as global stats and histograms, all sorts of histograms. We have the ability, if you are more into vibration, and if the data is unevenly spaced, we've got the ability to resample that. This contains filtering, and we can compute frequency spectra. For those of you who are more into durability, we've got cycle counting, rainflow counting, in other words, and fatigue damage assessments, online fatigue damage assessments, for instance. So all this within an app, and the way it's actually built is, again, using Python, right? So that's an example Python runner that runs in the backstage of an app. So the third challenge that nCodeDS addresses, or Aqira actually also addresses, is it's simple to use by engineers, because it's not enough to have the ability to process time series data with engineering algorithms. If an engineer doesn't or is not comfortable with using Python, that's your bottleneck then, right? So we want to make it as simple as possible to use for an engineer. So not all engineers are, again, very skilled with Python scripting, for instance. So the idea is there's whoever is writing it, potentially a data scientist or an engineer comfortable with scripting, and who's using it, right? So we want to use the Akira's feature called apps to turn that script into an easy to use app, right? That anyone could use, and that contains a very sophisticated analysis. So how would that work, right? You would start by first, you hide the code first of all, right? And you start by asking your user a few questions. So an app is constructed, right? So you can either ask your user to point to a specific set of files or folders, or you can use the data search, and as we'll illustrate during the demos. You can also ask your user to set some properties, right? Simplified GUI, where only a few properties are displayed. And again, this will be illustrated in the demo. And eventually, boom, you get your results. Simple as that. So select your data, either using a search or selecting the files, picking the files, answering a few questions like properties, what's the max you're looking for, what's this, that, and when you click next, you get your results. So that's a principle of an app. So that makes it easier. So we democratize the use of engineering data science to every engineer in the company. And it's no longer the very territory of a very skilled data scientist or something. That's the idea, right? If you want to know more about Akira, nCodeDS, or big data, check out our website. So we've got a dedicated page to nCodeDS, which contains a white paper on big data analytics in engineering applications. And you'll see a lot of webinars that have been recorded and that illustrate, the use of apps, or even what is Akira, or data search, etc. So don't hesitate to check this out. So in terms of conclusion now, and we'll move on to the demos right after this slide here. So nCodeDS enables an engineer to extract information from huge volumes of data, whether it's flat CSV files, whether it's a file or data that's contained in a database. We've got means to access, extract that information, and process it, right? The data is typically made of, it's coming from different data sources. It's not purely test and measurement data, but it contains all sorts of, coming from different inputs. So we do some kind of data fusion, and we address this variety of data. And being parallelized, etc., scalable, nCodeDS addresses the high velocity requirement as well. And that's quite useful for doing what if scenarios, especially if you are in a predictive mindset, right? You wanna test a few models and stuff. So high velocity is very crucial. But also, nCodeDS enables engineers to address the veracity. You remember, so I'm going through all the V's that we mentioned in the early slides. So we've got dedicated cleaning. First, we will detect any anomaly, and we'll when possible, we'll try to clean it or reject from the rest of the signal those anomalies, right? And we want to quantify the variability in the data. We can do that various means, but most importantly, nCodeDS helps you extract value, right? So you, as a designer, you wanna iterate, and you want to make sure your component is fit for purpose. You after loading information for your simulations, etc. As a reliability engineer, you will want to plan for maintenance, for instance, so understand what's the best strategy to adopt. So using historical data is probably the way forward. So that's it in terms of the PowerPoint presentation. Now we'll move on to a couple of demos, just two demos. I'll do one of them using flat CSV files, and Tudor, my colleague, expert in data science, will do the second demo, where he'll connect to an historian database. So let me start with the first demo. So just one slide to introduce it. So say I'm an automotive engineer now, and I want to understand how a population of drivers, of users of my cars, how do they use their cars in real situations, because we want to move to the next level of driver's assistance system, right? The ADAS. So where more and more of the usual things are no longer manual but made automatic in your car, right? So I've got CAN bus data coming from, I work for Peugeot Citroën, right? And I've got CAN bus data coming from various users. I've got tons of those data. They are CSV files, and they can, depending on the trip duration, they can be 10 meg or 200 meg or more, and I've got loads and loads of them. And if I open them up, I made it up. Those numbers are just fake, but just to illustrate the fact that some data is missing, some values are not realistic. In some cases, this happens with bus data typically, right? So, and in some of this data, those CSV files happen to find indeed anomalies of this type, right? So what I'm going to do now, what I'm after is to quantify how often a user exceeds the speed limit, and by how much. The idea behind this is I want, for instance, that's again a fictitious scenario here, but say I wanted to have an automatic speed correction built in, right? So I need to know, I want this automatic thing to happen in a comfortable fashion. I don't want my drivers to be surprised. I want it to mimic more or less a real usage. So I need to quantify the speed and how often it exceeds speed limit. Another thing I want to do is implement automatic brake if the distance between vehicles is too small. So I want to quantify the distribution the distance between vehicles, and probably more interestingly, the time gap between vehicles. So let's do that. Enough talking. Let me just move on to the demo here. So I'm using now my web browser, and I'm logging to my Akira system. I've got a login and a password, and I'm logging in now. So I'm logged in as Fred Kim, and you'll see in a minute that I've got a dedicated dashboard. That's my dashboard. It's showing me the latest results, whatever usage, and so that's Akira. I won't insist much on Akira. Again, there are webinars showing you how this works and all the benefits in using Akira. I'm gonna jump straight into my list of apps, and we're gonna run. So I've got a few apps here, and we're gonna run this one, process CSV files. So I'd like to acknowledge the collaboration of a PSA group here. So they indeed provided us with example files, and we discussed this fixture scenario together, and they allowed me to use their name and some of their data for this demo. So let me just run this very app. So you won't see a single line of Python. You won't see anything complicated. Hopefully, what you will see will be a series of questions, basically, and some reports eventually. So the questions here, as the author of the app, I've set that up such that it's as easy as possible to use, with a title and some drop-down menus, etc. So I'm going to choose a car. So let's go with the DS7. Beautiful SUV. Drive type, yeah, that's fine. And a model year, I think 2018 that's where I've got most of the data. I'm pressing next now, and there is server-side processing going on. So that's actually hosted in an Azure system. So in the cloud, nothing's running on my local machine. It's all run remote on big computers, right? And that's it. I've got my report. So let's just open this one up and let's see what's in there. It's a PDF. So that's my vehicle. So that's my report, basically. Total distance driven, 700 kilometers, representing 850 minutes of driving. And I've got here my distribution of speed, limit exceedance, actually. So that's the speed difference between the current speed and the speed limit. So it implies that in the CAN data, you've got the knowledge of what's the speed limits. And this is done thanks to the directions, the recognition of, so that's video processing thing that is embedded in the car and provides you with this information. What's the current speed limit in the CAN stream? So we've computed the difference, and we've computed this histogram showing how much time do we spend below the speed limits, and at which sort of difference in speed, right? And how much time do we spend beyond the speed limit? So the PSA users are mostly below the speed limit, but there are certain users that go up to, for a few of them, up to 50 kilometers per hour above the speed limit. So that's quite informative, I believe. The other histograms. So this one is showing the distance between vehicles. So we see two distributions there, close to I'll say very, very short distance between vehicles and beyond 250 meters. So looking at it, I'm like, maybe this this distribution here is mostly for like high traffic. Most of the data was coming from the Paris area, and so maybe it's bumper to bumper type conditions. So the other interesting histogram to look at is the time gap between vehicles. That's probably more interesting to look at, because it contains it takes into account the speed, actually. So what we have here is most of the case, there's over 6 seconds between two cars, but there's this scenario that's not rare where there's between 1 and 2 seconds between cars. So that's just an example of what can be achieved from huge quantities of bus, CAN bus data, to really understand, grasp the usage of a car. How do a vast panel of users use their cars, and to extract statistics and usage information from that. Let me go down now to my PowerPoint, and we'll move on to the next demo, which Tudor will be presenting. So Tudor, it's all yours.
Brilliant. Thank you, Fred. So in the previous presentation, Fred showed how it is possible to access a large number of files and analyze data stored in files. And this is a very important use case, because traditionally this is how data is stored in engineering organizations. However, it's not the only possible way of storing data. There are multiple technologies out there called historians, and these are specialized databases that allow you to organize and query your data. Again, they're not file based. They are a lot like databases, and it's not something that we offer, but it's something that we can leverage in order to simplify our data management and subsequent analysis. So let's look at a possible problem, engineering problem. Suppose that you have a fleet of vehicles which are continuously recording data, and suppose that this data is stored in a data lake, which is external to Aqira. Now, the question is, how can I extract interesting information from the data lake? And on top of that, can I leverage some of the capabilities that are offered by this historian database, by the data lake that I'm using? The interesting thing is that once we start looking at different types of data sources, so not only files, we begin to understand that it is possible to combine information from multiple sources, such as, for example, weather data, if we are interested in, say, the operating conditions or the environment for our assets. So using nCodeDS, it is possible to combine engineering data, other data sources. I mentioned here environmental data, but we can also have maintenance records, and create interesting engineering results. Now I'm going to move to a demo in Akira. So in this system, we set up an external influx database, which we will query using nCodeDS. So, as Fred mentioned earlier, nCodeDS consists of standard engineering algorithms and file accessing functionality, which is available off the shelf. But it is also possible to extend existing functionality in nCodeDS using Python, so that you are able to either plug in your own data analysis algorithms, or you can create your own data access functionality. In this case, we use this functionality to access InfluxDB. So I've just started the app for analysis, and even though Influx is a relatively complicated product to use, I was able to build a relatively simple interface to it in Akira, which is, you could argue, very intuitive. So in this database, I have data from 10 vehicles recorded over a year, and I can choose to perform specific analysis on that. So here on the leftmost side, I have the vehicles that I want to, say, extract data for. Let's say that I'm interested in the speed channel, and suppose that I want to perform time at level for the speed channel. Optionally, I can include weather statistics. This might be interesting, for example, if you are designing trucks and you want to estimate what lateral loads are exerted on your vehicles when they are being driven in certain conditions. And let's suppose that I want to extract all the data from April. So all the coding for this and all the setup has been done in the background. It is possible to use the application just how I'm using it right now, without going through the details of how this was implemented. And this is an important feature because the person who wrote the app and the person who used the app don't necessarily need to be the same. So without further ado, let's let nCodeDS extract the data and then perform the analysis. So as we speak, InfluxDB is querying the data based on the parameters that I specified on the previous GUI page, and it pulls the results. And once the results are available in nCodeDS for processing, then it continues with the engineering analysis. So here I have the time at level for the vehicle speed. I also pull some weather data. So we have analysis for that as well. So this is the end of the demo, and I guess that the takeaway is this: you can access your data sources, whether they're files, historians, or other entities, using nCodeDS. nCodeDS has the built-in functionality that allows you to extend your analysis with code, be it to execute bespoke analysis algorithms, or to simply access your data sources. So that's the end of the presentation for me. Over to you, Fred.
Thank you very much, Tudor. Just a question for you, Tudor. You mentioned accessing data from a database or files, or the weather information that you used here. Isn't it accessed by interrogating a website, weather conditions or something over the web?
Absolutely. So it is definitely possible to access data this way, because it is a Python API, which we can easily integrate in nCodeDS.